Good morning, Dickie. How you doing? I can't hear you though.
Fuck. Sorry. I'm I'm good, thank you very much. Just sort of just been a bit of a busy day, but that's okay. It's fine. We're here. Everything's fine, I think.
Yeah, I think so too. And my colleague Sandy Delgado has joined us, and behind me is Delon Jarawala. So Delon, meet Dickie Whitaker. He runs the Lighthill Risk Network and is providing your funding for the position. Yeah. So yeah, I think we're all set. I'm gonna go be right back, but I think we're ready to go. And I think I can just when you're ready, I can share my screen then.
That's cool. That's good.
Okay.
Well, okay. And I mean, it's pretty informal, but so you can say obviously, I don't, you don't need any ideas. I just occurred to my head this morning. I was thinking, like, I wonder how long you are going to speak for, but it's whatever it is, it's going to be interesting.
I think it's going to be around 35, 40 minutes total, something like that, if that's okay.
That's fine. Yeah. Between
Great.
the two of you, yeah.
Awesome. Yes, between the two of us. Right. All right, great. Well,
Okay. I'll
I'm admin. Hello.
Good morning.
Hello. Good morning.
Good morning for us. Yes. Good afternoon.
Good morning for you. I suddenly thought, well,
Correct.
today got
Sorry about that.
started again.
So we'll just thanks everybody for those of us who dialed in a minute early. We'll just wait till everybody joins in. As you're going to handle the lobby.
Yeah. I'm on the lobby. Got people coming in.
Hi, Joe.
Hi, Dickie. Hey, Chris. Hi, Tula.
Good morning. Thanks for joining in. All right.
Hi, Rick. Good to see you again.
Rick, you're in the mountains. You're on mute.
Sound doesn't
yeah, I
show.
always use a mountain background. It's kind of Zurich-y, you know. It's near us anyway. It's actually this time of year as well. It's May. Ski tour in May. So
Oh, lovely.
recently. Yeah.
I think we're expecting about 70, so wait a bit more.
Hi, Valerie. Good to see you again.
Hi everyone.
Have some European agencies in the space. That's good too. Too many people to say hi to. Just going to give it a couple more minutes and then we'll kick off.
Yeah, so we have the spatials on Browse. It's open plus that. Yeah.
Give it one more minute and then we'll start, and then people will only miss my introduction, which won't be too bad. Kick them out, Chris. Let's kick off. Let me kick off anyway, and then we can let others come in. So welcome everybody. Thank you for joining. I was just saying to Chris earlier on that I think this is a fairly relaxed sort of conversation between us. Although, you know, bits of this are really important too. I mean, so the conversation may be relaxed, but the reason behind this is important. And the starting point for this was a conversation that that Chris and I had probably 18 months ago, I'm guessing about now, because there was some more research work needed to be done, principally to HURDAT, and there was an opportunity for a partnership between a student, possibly at that point to be decided, and some insurance industry participants. And so the Lighthill Risk Network, which I co-founded 20 years ago or something, was keen to support that, and that's a group of companies that includes Lloyd's and Aon and Guy Carpenter and Amlin and Liberty Mutual and Hiscox. So they decided to fund a student to help with HURDAT, which sort of obviously probably for everybody on this call is just such a fundamental importance to all of us. And so the work that NOAA and has done in this space, and other federal agencies, and in fact other European agencies, it's what makes our world tick. So in one level, this is a relaxed conversation. On the other hand, this is a really important part of how the insurance and reinsurance industry understands risk, which is the foundation of everything we do. So I'm really pleased that we can have a quick conversation between Chris and some of his colleagues about what's going on here, what's happening to HURDAT, and specifically some research into why HURDAT needs continuing research to make it useful and suitable for our needs today. So that's enough from me. And unless we've got one hand up, is anything problematic from Dante, or is that an accident before we move on? I'm assuming it's okay. Write something in the chat and we'll do some Q&A at the end of this. So Chris, over to you.
Great. All right. Can you all hear me and see my screen?
Yes, we can.
Great. Okay. Well, again, my name's Chris Lancy. I'm a branch chief for marine forecasters here at the National Hurricane Center in Miami in the United States. And I really appreciate the support that the Lighthill Risk Network has been providing for us to continue this applied research. And so today we're going to talk about some of the challenges and opportunities of collating a clear picture of historical hurricane activity. Specifically, we're revising or reanalyzing the 1974 hurricane season. And so this is work that many folks are contributing to currently. I'm kind of the orchestra conductor, and Dilan Jarawala, who you'll be hearing from, is University of Miami undergraduate student. Sandy Delgado is one of our forecasters here at the Hurricane Center. We have two volunteer students also from Florida Gulf Coast University on the west coast of the Florida Peninsula, Ella McConnell and Abby Idzik. And we have a high school student that's also volunteering, Aaron Blonsky. So with that in mind, I'm going to talk about what HURDAT is to begin with and why we need to revise it. And then Dilan's going to go into some of the details about what we've been finding for 1974. So HURDAT is the hurricane database. So it's been around for about 50 years now, and it was originally developed to help support numerical model track forecasting of where hurricanes are going to go. And the database goes back to 1851. It goes up through present, 2024, all tropical cyclones. So that would include depressions, tropical storms, hurricanes, as well as subtropical storms, which are kind of hybrids between regular hurricanes and extratropical systems. The format is that the database has all known storms, which is an important point because, as we're going to make a point, we are finding new storms back in the 1970s that occurred, but people hadn't put together. And so for every known storm, every 6 hours, we have positions to the nearest 0.1 degree latitude longitude, so about 10 kilometers. Intensity, which is peak surface winds, and a central pressure when it's observed. So that's the lowest pressure in the eye. And then wind radii. So the size of the storm is more recent. That's only since 2004. And then radius of the strongest winds just since 2021. And so that's what HURDAT is. There's a paper that I co-wrote a decade ago that talks about the new format that we have for providing this. So where is it used? And Dickie mentioned that this is kind of a foundational data set for you all. That's true for many folks. We use it here at the National Hurricane Center to validate our official forecasts as well as the model predictions. It's used for climate trend assessment, looking at interannual variability, decade to decade changes, and long-term aspects, including climate change, trying to understand how that's evolving. It's also used in the insurance industry, as I'll show, and it's used by engineers for figuring out what building codes are the best appropriate for the coast and inland. And it's also used by emergency managers for them to know what the worst storm is to prepare for and how often they would have hurricanes making landfall locally. But on the business side, worth pointing out that this is really foundational for catastrophe modeling. And so, for example, this graph from the Florida Public Hurricane Loss Model, upper right corner is the hurricane database, and that's what feeds into everything else when it's the frequency of return for different storms and different strengths, and then the engineering component, and then the economic component. But it all starts off with HURDAT. So the more accurate and more complete we can make this hurricane database, the better it is for all these users, whether it's meteorologists or climate change or engineers or on the insurance side of things. So I did want to talk about some of the ways we measure hurricanes, both today and in the past. And so today we're very fortunate. We've got these incredible in situ measurements, measuring locally what's going on in hurricanes, but also remote ones from space. So for example, we have ships and buoys, both moored buoys and buoys that drift around, providing measurements. And there's measurements from space. And so these wind barbs are from the European Space Agency's scatterometer, as an example. And so we really have an incredible database available to us. Additionally, we've got both geostationary satellites that gives us coverage every couple minutes over the entire hemisphere, both in visible wavelengths as well as infrared. And then there's polar orbiting satellites that are orbiting the Earth several times a day, and they can look in the microwave spectrum and see through the upper level clouds, which is important because hurricanes are fueled by the thunderstorms, and this allows us to actually see that structure. And so these are great tools that we use every day right now. In addition to that, there's aircraft reconnaissance. And today, two main aircraft that fly through the storm center are the NOAA P-3s and the Air Force C-130s. And they fly through to find three main aspects. Where is the center? What are the strongest winds in the eye wall, which is the kind of donut of strong winds and heavy rain near the center? And then how large is it? That is, how far do hurricane winds and tropical storm winds extend from the center? And so we're very fortunate to have both the satellites and the aircraft today. And in the end, every day from June 1st to end of November, we're doing our day-to-day forecasting here at the Hurricane Center. But after the season, it's the hurricane specialist's responsibility, whether it's Eric Blake or Robbie Berg, to individually work on storms to go back and say, well, when did it form? What was its genesis? When did it dissipate? Where was the actual track that the storm took, and what were the peak winds and the sizes? And so while it's not the main thing we do here at the Hurricane Center every day, it's a very important, you could say it's a byproduct of our operations, but we realize how important it is for so many users. So much of the off season is spent on reviewing the last season's storms and making sure that database is as complete as possible. So when one is trying to use this database going back in time, we didn't always have the great tools that we do today. And so many of those that I've mentioned, have only been available fairly recently. So one key tool, for example, is the step frequency microwave radiometer, which is an instrument mounted to the airplanes that looks down in the microwave spectrum and can figure out from the spray, and it's emitting microwave radiation, how strong the winds are. So that's one example. You go back further in time, we didn't have accurate winds aboard the aircrafts. It was really starting in the late 80s was when we first had accurate winds aboard the airplanes. Satellites started in the early 1970s for providing quantitative information about where the storms were and how strong they were. So you can see further back in time, the data sets are fewer and far between and less accurate. So it's important, especially if you're looking at climate change, we really have some great tools in the toolbox for determining how many storms, how strong they were, how long they lasted. But as you go back further in time, it's much more difficult. And in the era that we're working on now, 1974, it's kind of in between. We're starting to get some of the modern technology, but still had a lot of limitations. So why revise this database? You know, it goes back to 1851. Isn't it perfect now? Well, the reality is no, it's far from perfect. There's biases and there's also random errors. And so, for example, one of which was originally the Saffir-Simpson hurricane scale was based on central pressure. That is the lowest pressure in the eye. But nowadays, since we can measure the winds more accurately, we use what the winds are. And so part is, as we've been going forward in time, is to change the Saffir-Simpson hurricane scale designation to make it based on winds. Another issue was back in research I did in grad school, there was a bias in the number of major hurricanes. They were kind of overdoing it back in the 40s, 50s, and 60s because they were using the eyeball estimates from the meteorologists on the plains to figure out how strong the winds were. And we realized that it was a little bit overkill. Another aspect is missing storms, storms that occurred. There may have been vessels that went into them, but no meteorologist ever pieced together that those existed and were tropical or subtropical storms. We're also adding in landfall parameters. The original hurricane database, or HURDAT, didn't have landfall information. It only had information every 6 hours. And so we're adding in those as we're going forward. And then lastly, there's advances in our scientific understanding of the structure of hurricanes. And this example here is one of the dropsondes, one of the instruments that are launched by the aircraft. So starting in the late 90s, they had GPS versions of these, and they could really accurately measure the winds all the way from the flight level until it splashed in the ocean. And some work that James Franklin and Mike Black did back in around 2000 was able to take accurate flight level winds and then adjust them to the surface. We actually call it the 90% rule. And so now we can apply that going back further in time as we reanalyze. So these are some of the reasons why it's important to re-examine the existing hurricane database. So just a couple more words, and I'm going to hand it over to Dylan here. So the data sets, as I mentioned, we try to grab all the original observations. The HURDAT is more of a synthesis, but it doesn't have individual measurements. And so that's the key, is to have a good synthesis, you have to get all the original measurements. Once we do that, we put everything into a single database, and we conduct an analysis 4 times a day. And then we redetermine the formation or genesis, the dissipation, where the storm tracked, the peak winds, structure. Was it tropical? Was it this hybrid kind of subtropical? Or was it kind of more of a winter storm structure? And then we document everything because we want to make sure that the changes we're doing are transparent. So if somebody 30 years from now says, well, that crew that Lancey was doing, they didn't know what they were doing, they can actually go back to the original file and start over if they wanted. And when we're doing these revisions, we actually hand them over to a committee that Dr. Jack Bevan leads to independently check on these revisions that we're proposing. So there's kind of a sanity check to make sure that this meets the standards of the actual hurricane specialists that are out there. So I hope that's a good kind of preamble. Maybe I'll pause there and see if there's any questions about what I presented before Dylan gets into the specifics for 1974.
Chris, thank you. If you're going to do questions, just because of the number of people, it's probably easier to just put it in the Q&A. See a hand up, we might not. So, and if not, we can do some questions at the end.
Okay.
So far, so good. That's
all right. Well, great. Well, then I will hand it over to Dylan, and he'll talk about 1974.
Seamless transition. Different chairs.
All right. Can everyone hear me?
Loud and clear.
All right. So my name is Dylan. I'm a student at the University of Miami. So I'm here to talk about what we've done for 1974 and how we use the different types of observations that Chris mentioned to determine how, if any, changes need to be made to the HURDAT database. So the first of these observations I'm going to talk about are the NHC microfilm analysis archive. So even up to the modern day, there's always been a unit of forecasters at the NHC mouse not working, that conduct surface analysis. They take a look at all the available data, including ship observations and observations taken at land stations like these over here. See this one over Nicaragua, and essentially make pressure contours, telling forecasters this is a line of constant sea level pressure. So all the sea level pressures along this line are the same value. So this essentially outlines where storms are, where high pressure systems are, where low pressure systems are, and Computer also is a first look at where what the type of environment storms are located in. So in this example here, you can see this in the reanalysis, this microfilm analysis from September 19th, 1974 of Hurricane Fifi as it was approaching the north coast of Honduras. You can see that there's a lot of peripheral observations, but very few near center. So these are pretty good for getting a first guess at where the storm might be located, but not so great at getting intensity information. So the next tool we have is satellite observations. So starting in 1974, we had the SMS, that's one of the first geostationary satellites that had both visible imagery and infrared imagery. So we had around-the-clock coverage of what the planet looked at any given time. So the SMS imagery that's available to us, there are every half-hour snapshots of what the Western Hemisphere looked like. So this is, again, Hurricane Fifi north of Honduras. You can see there's a lot of spiral banding. This is something we would not have been able to see without the satellite imagery. And you can see, if you look carefully, there's little pencil marks outlining parts of the storm. So those pencil marks were made by analysts in 1974 conducting a very early version of the Dvorak technique, which is still used in the present day to subjectively analyze the intensity of storms following some set guidelines. Now, the intensities assessed by these forecasters in 1974 are still available to us today. And we can use that along with what we've learned since 1974 to make better guesses about what a storm intensity might be based on just satellite imagery. The next piece of information that we have at our disposal is aircraft reconnaissance. And I think aircraft reconnaissance is probably the most important sort of observation that we have in order to guess the intensity and location of a storm at any given time. Because a lot of times storms don't go near areas that have considerable land observations, because storms tend to happen in the middle of the water, and tend to weaken by the time they get to land. Now, the other part is that ships don't like to go near the center of the storm because that's not great for ships. Lots of strong winds and heavy rain, not great for shipping there. So great thing we do is we fly planes into hurricanes. So in 1974, there were 3 agencies flying aircraft reconnaissance missions into hurricanes, compared to the 2 today. So we had NOAA, and they still fly today, and Air Force, they also fly today, as seen here. They also did Navy, though. So the Navy is, as you see here, this is the Navy mission to Hurricane Carmen. They no longer fly missions into aircraft, which is unfortunate, but that was available to us in 1974, and we were able to use that information to estimate the storm intensity better here. So the aircraft reconnaissance missions, they collected 3 principal types of data sets. The pressure observations, the flight level wind observations, and surface wind. Now, of these three, only the pressure observations are considerably reliable and useful for our analysis because the flight level winds were often attenuated by heavy rainfalls and were not considered pretty reliable. And surface winds were still visually estimated for a time period, which, well, when you visually estimate wind speeds, you can often mess up because, well, you're not actually measuring anything. The next tool we have at our disposal is radar imagery. So the radar is only available when a storm passes near a land-based radar. So, for example, this loop here is from Belize City, and someone decided to archive the imagery. So a lot of the early radar imagery is not available anymore because no one decided to archive it. They maybe decided it was not too relevant, not too useful. For a couple of important storms, there are sets of photographs essentially that were taken of the radar loops, and we were able to piece that together. The original data sets, the original radar pictures that we have, they do not have any latitude longitude information on them. But since they do have range rings corresponding to a fixed number of distance away from the center, and we have a good idea of where the radar was located, we could reconstruct the location of the storm relative to the radar position and, well, land, and get a good idea of where the storm was at every given point. So this is a radar loop we reconstructed of Hurricane Carmen, 1974, making a landfall in near the Belize and Mexican border. You can see its secondary eye wall formation going around here as we move into land. Notably, this was really helpful for figuring out what to do with the intensity of landfall, because operationally they use observations of this city, Chetumal, here as the peak intensity at landfall. So they used an intensity, I believe, 125 knots and 952 millibars. Observation at Chetumal was 118 knots and 952 millibars. And it was unclear, there's a lot of ambiguity as to whether or not those two observations were co-located. Now, you can see here, the eye of the storm actually passed to the north of the city. So minimum pressure was probably not at the same time as the strongest winds. So minimum pressure was probably lower at the closest approach to Chetumal, indicating our storm was probably stronger at that point. All right, the next piece of information we have at our disposal is some relatively new, and it's plotting the ship observations on top of model reanalysis. So this over here is the East European Center for Medium Range Weather Forecasts 5th generation reanalysis data set, the ERA5. This is surface wind speeds, and I've also plotted on top of that ship observations from the ICOADS data set, which Chris mentioned earlier. So this data set, in 1974, you didn't have real-time communications between the ships and the National Hurricane Center. So not all observations made it to the Hurricane Center in time for the forecasters to make their surface analysis, the microfilm analysis I showed earlier. So now that we're in 2025, we have access to all those observations, so we can reconstruct what the storm's wind field might have looked like based on those extra surface analysis that are missing in operational times. So we can compare the temperature field, the dew point field, and the wind field, and the pressure field to what's reanalyzed on the model data set, and essentially figure out what a structure of the storm was. Was it more or less tropical, more or less subtropical? How big was the wind field? Do these observations make sense near the center? And many other pieces of information we pieced together from this data set. All right, so next I'm going to do is I'm going to cover one specific storm, probably the most notable storm of the year, Hurricane Carmen, which was a operationally Category 4 hurricane and made landfall in the Yucatan Peninsula, as I mentioned earlier, before reemerging over the Gulf of Mexico and intensifying again to a Category 4 hurricane landfall as a Category 3 in Louisiana. So I mentioned a lot of different types of data, and we collected a lot of different types of data stored here at the National Hurricane Center. So all those black data points here are over here, a lot of radar fixes. These are all aircraft fixes and satellite fixes all the way through over here. So this is plotted using the Automated Tropical Cyclone Forecast System. And for the first time, we will be making these data points available to the public. So they will be able to piece together, what information we have to reconstruct the storm's track and intensity and see, did what these guys do make sense or did not. So what I'm going to do now is show the original track and the revised track. So original track, revised track. So there's minor differences in positioning, the storm was very well observed throughout its entire lifetime, so there isn't much of a need for large changes in position. You can see there's some changes in speeds south of Puerto Rico when the storm wasn't well defined, as well as some nudges in track to the east and west in the Gulf of Mexico, possibly caused by high degree of parallax angle in the Gulf of Mexico because the satellite viewing angle was not great. Otherwise, the track was more or less consistent with observations and what the original track was. The same is not necessarily true for intensity, though. So there are some significant changes in intensity throughout the storm's lifetime. Again, this is a preliminary analysis, so it is might be revised again before being set out to the general public. But you can see here that there's now a additional peak intensity ahead of the main peak intensity, which is over here. Based on aircraft reconnaissance data, which showed an additional peak intensity where it very quickly intensified to about 110 knots before weakening again abruptly and re-strengthening to its main peak, which has been raised a bit to 140 knots. Now, the other major change was a little bit faster weakening over the Yucatan Peninsula and a lot weaker over the Gulf of Mexico because the surface pressures observed by aircraft did not align well with the winds that were assessed by the storm. Now, the winds that were assessed operationally were derived from the visually observed winds, which are, again, as I mentioned earlier, not very reliable. Just summarizing what I just said, so we added an additional peak at 9Z on September 1st, and as well as the subsequent weakening and re-intensification to the main peak, 140 knots. The peak intensity is now at 3Z, and we now show it to weaken before the landfall in Belize based on the aircraft data. And based on the decay relationship of tropical cyclone pressures and winds, we adjusted the intensity downwards over the Yucatan Peninsula and have made major changes to peak intensity in the Gulf of Mexico and extended the track a little further inland over the United States based on the surface analysis, because the surface analysis showed a coherent low pressure system further inland that was previously analyzed. Right, so altogether, here are the changes that we made in the 1974 season. So this is the original seasonal map made in 1974, and this is the revised map. So notice there's a couple of new storms here. So there's one storm out to the east of Bermuda that was not there before, this subtropical storm, number 13, as well as this system in the Gulf of Mexico too, over here. And there's some other minor changes to intensity, whether the storm is tropical or subtropical, whether it's not a storm is classifiable or not at some point of its life. You can see another major change was what happened to Fifi over here. We judged that Fifi and Orlean of the East Pacific were actually the same tropical cyclone. So Hurricane Fifi made landfall in Central America, crossed Mexico, re-emerged in the Pacific Ocean, and re-intensified into hurricane before making landfall in Mexico a second time as Hurricane Orlean. So just a summary of all the changes made. So originally 20 tropical or subtropical depressions analyzed in 1974. So 50 years later, we recessed that to be 17. 11 tropical storms or subtropical storms operationally. We revised it upwards to 14. And the number of major hurricanes is essentially the same, 2, but they were both up by around 5-10 knots to make them like Category 4 and Category 5 respectively. And the 4 hurricanes are still there. So just reiterating what I said, on top of what I mentioned earlier, several weak depressions that were there in the data set were just never been classifiable, which explains why the total number of storms went down from 20 to 17. And because of the reanalysis data sets from the ECMWF, we were able to make a lot of adjustments to this classification status of storms, as well as comparing that to observations. All right.
All right. Great. Okay, so as Delon mentioned, we're adding new storms, 3 brand new tropical storms, removing a few depressions, and in general making minor changes to the existing tracks, but sometimes much larger changes to the peak winds, sometimes up and sometimes down. So I think we're adding accuracy. We're still not going to have a complete database, but we're hoping it's much more complete. And so where we're at now on this reanalysis effort, I've been involved with this for 20 years. And we have currently, we had revised 120 years worth of systems up through 1970. And now we've gotten 1971 through 1974 preliminary reanalyzed. Typically, I wait to have a 5-year chunk before providing it to the community because it's just too much work otherwise to make it available every time we have a single season done. And the need for doing a reanalysis really needs to be all the way through the year 2000, because that's when the 90% rule came into being. But it may be that it's needed all the way through the 2020 time period because of issues with the step frequency microwave radiometer that are still plaguing us today. So we're moving ahead on all that. And as we provide these reanalysis, we've been systematically publishing them in the peer-reviewed literature as well. And so once we finish up through 1975 and make that available to the public, I'll put together a journal article to send to Journal of Climate as well. And then just lastly, thank you again for the funding that we've been working with you all to continue these efforts. So Dr. Lisa Murphy-Goes from University of Miami is is in charge of the program for the proposal. And I'm kind of an unpaid advisor. I get paid well enough in my federal salary. And it took, as Dickie knows, and Lisa knows, it took forever to navigate both the federal system as well as the University of Miami system. The paperwork was really rough, but we got through that. And DLON's been working really hard for several months now. And so I think we are on track to having this draft essentially done now for 1974, and 1975 we should have a draft done on that by the end of the summer. So I guess with that, any questions for DLON and I?
Well, there are a couple in the questions, and yeah, sorry, I think you pretty much answered one of them already, I think, but it's just like, why 74? Well, 74 is where you got to, right? I think that's the answer there.
Right. So for the first 12 or so years that I was working on this project, I had funding from the U.S. Climate Program Office, but that they switched emphasis to doing almost exclusively computer modeling simulations, and not as much funding for observational studies. And so the last several years, it had just been myself, a couple volunteers, and a couple of the forecasters. But as our operational duties take precedence, we had not been able to make much progress. So having this funding from the Lighthill Risk Network really is great, because DLON is a budding superstar, and having him being able to devote time on it is great. I'll point out this really nice graph that he did for this combination of the model and the ships on top of it. He just came up with that on his own. And so that was really a great time saver for us in examining both what is a reanalysis model show, as well as the actual ship observations. So thank you again.
No, that's good. Look, there's another question here, which from Nick, which is about, hang on, if I can just get rid of this. So you sort of, again, I think, well, partially answered this, but if these changes are accepted by the NHS Best Track Committee, are they eventually going to be incorporated into IB tracks?
Oh, yeah. I work closely with the folks at IB Tracks. Ken Knapp had been the PI there. He recently retired, but there's a new person in Asheville, North Carolina that's doing that. Yeah, anytime we add in a year, like the 2024 hurricane season, I send them the HURDAT 2, and they incorporate that fairly quickly into IB tracks. So we make sure that those are consistent.
Good, that's good, which we, of course, as an industry, use a lot. Any other questions from people online? Just stick it into the Q&A tab at the top, and we can look at those. I mean, I suppose I've just got one observation really well, which is just waiting to make sure we got one new one here. But just quickly while I do that, which is, as it isn't surprising, I suppose, that we get these changes if you think about it, but it just underlines the importance, because I mean, I think most years you get some, reasonably significant changes, right? Up or down in number of tracks. I mean, this matters to get this right.
Yeah, I think so. There's always questions about how is climate changing, natural variability and man-made. And the difficulty in assessing those in the HURDAT itself is that technology change is as big or bigger than the climate change. And so if we can make a more homogeneous database, then that helps in those assessments there. And so again, it's not going to make it a perfect database, but it's going to be substantially improved. And the approach then becomes more homogeneous over time, and then less of an influence on the technology change.
Yeah, absolutely. Ioana's got a question here. On the slide showing the model reanalysis and ship observations, I think you mentioned this allowed you to figure out if a storm was subtropical. Do you mind explaining how?
Right. So a subtropical cyclone is kind of a mixed breed. And so they typically have asymmetric convection, kind of lopsided thunderstorms on one side. And they tend to have a very large radius of maximum wind. So a hurricane may have a radius maximum wind from, say, 10 to 50 kilometers, but a subtropical storm may have it 1 to 300 kilometers. And then lastly, a subtropical system is assisted by an upper level trough that helps to force it. So it's those three aspects that differentiate it. Plus, they typically don't reach hurricane force. They stay between about 30 knots and 60 knots typically.
Good. One more here. This is a technical one, I think, really. Can you speak a little bit more about the issues with the step frequency microwave radiometer?
Yeah. So the SFMR it's a really unique instrument. It's got 6 different frequencies that it monitors from the airplane. And as the ocean is churned by the winds, it emits a little more microwave radiation. And so it's not enough to cook a hot dog on the airplane, but it's enough to calibrate and get what the winds are. And it works really well from about 50 knots to about 100 knots. Below 50 knots for like depressions and weak tropical storms, it gets confused if it's rain or wind or both. And so it tends to overestimate the winds at the low end. At the high end, the original work that was done by Eric Uhlhorn and Pete Black didn't have very many data points, so it wasn't calibrated very well. And what we've been suspecting here at the Hurricane Center is that it's high biased. And so right now, we're actually downplaying the use of it because of that uncertainty in the calibration. We're hopeful that the researchers can get that figured out. So one of the researchers, Heather Holbook at the Hurricane Research Division of NOAA, is looking at it. Also, Paul Chang at NESDIS, the satellite group in College Park, Maryland. So they're trying to work on that. But right now, it's I don't know if it's intractable, but it's proving to be very difficult to get that reliably calibrated.
Thank you. Good. Anybody got any more last questions before we finish off?
And Dickie, I'll send you the presentation so you can feel free to forward it along to whoever you like.
Oh, that'd be marvelous. Thank you. That'd be fantastic. Well, look, maybe let me just round this off, and we'll say thank you everybody who's dialed in. That's much appreciated, and thanks for some good questions. Thank you for the team, Chris and Dylan and everybody else who's made this work, and Lisa for getting through the bureaucracy. In a future life, I'm going to simplify funding between academia, national institutes, and the insurance industry. That might be a goal worth going for. But for now, look, we just want to say that we're so supportive of what you're doing. We really appreciate it. And please do reach out. If there's anything else we can do in the future, and we hope to meet this side of the pond or that, and look forward to buying you a drink somewhere or other to say thank you.
Yeah, sure. And if any of you all, come down to Miami for business or pleasure, we're happy to give tours of the National Hurricane Center as well.
Sounds like something that we should take you up on at some point. Thank you so much. So I think with that, I'm just going to say thank you all. And on behalf of Lighthill Risk Network and Oasis, we'd just like to thank everybody for attending and for speaking. Thanks all, and see you all soon.
Great. Thank you.
Bye-bye.
Many thanks.
Bye. Thank you.
Thanks a lot. Bye.
Thank you. Bye-bye.